Hi everyone, my name is Farzam Duruskar and I will be presenting ThreadMonitor, a low overhead data rate detector for C++ applications that uses Intel processor trace. I'm a third year PhD candidate at Dorsal and currently at our lab we are working on different topics related to tracing and program verification. We have teams working on monitoring and debugging of high-performance distributed heterogeneous systems. We have a PhD candidate who's been working on GPU tracing and profiling. We have another PhD candidate who's working on scalable trace analysis and visualization. I'm the one working on low overhead runtime verification, and we also have PhD and master students working on machine learning approaches for analyzing traces. The project in a nutshell, as I mentioned, TMon, ThreadMonitor, is a post-mortem data rate detector for C++ applications that use pthreads. At runtime, it traces the required information for data rate detection using Intel processor trace. And then when the execution is finished, it analyzes that trace data to determine whether the traced execution exhibited a data race or not. As we will see, it has no direct impact on application memory usage, and it also has a very low runtime overhead. So here's the agenda for this presentation. I will start by a quick introduction to what is a data race. Then I will continue with explaining the motivation behind our research. And after that, I will get into our methodology and how different parts of TMon have been implemented. And finally, we will see our latest results and also a section on conclusion and possible future work. What is a data race? In multi-threaded programs, threads typically share access to a portion or the entirety of the program of the application memory. Although shared memory enables efficient thread communication, but it also exposes a multi-threaded program to data races, which happens when two threads access the same memory location without a timing constraint ordering the two accesses, and at least one of the accesses is a write operation. And by timing constraints, we mean both of its forms, which are synchronization or mutual exclusion. And here's an example C program with two threads accessing a global variable without a timing constraint, and therefore we have a data race. Note that in this example, the final value of the shared variable depends on thread scheduling, and that is how data races can cause non-determinism. And if such behavior is not a design choice by a programmer, then a data race should be considered a concurrency error. What was our motivation for doing this research? First of all, we should note the general importance of automated data race detection. Detecting data races can be an extremely challenging task for programmers due to two main reasons. First of all, a programmer needs to ensure that every access to shared memory follows proper timing constraints, which can be very complicated even for a relatively simple project. Second, in the presence of a data race, sometimes only particular thread interleavings may lead to the corruption of shared data. So even with comprehensive testing, it is still possible for a programmer to miss a data race. And further, a corrupted shared variable does not necessarily lead to immediate failure, but it might propagate through the program and eventually manifest as some unexpected behavior in some other parts of the program, which can be very hard to debug. But why a new tool? Because the state-of-the-art tools, specifically ThreadSanitizer, which is an on-the-fly data rate detector, the default data rate detector for CLang and GCC, because they impose incredible runtime and memory overhead. With ThreadSanitizer, the average slowdown is reported to be between 5 to 15 times, and the average memory overhead is reported to be between 5 to 10 times. And it is even, on average, it is even worse for other well-known tools like Hellgrind. And due to this fact, these tools cannot be used in many real-world testing environments. Like some of our industrial partners cannot afford such high overheads. Therefore, although they would benefit from, for instance, the comprehensive analysis performed by ThreadSanitizer, but they cannot simply use it. And that is why we decided to work on ThreadMonitor, where we defined our main goal to be to design a data race detector that is capable of performing the same analysis as ThreadSanitizer, but with very low overhead. We designed TMon as a post-mortem tool, which means it traces the execution of your program using Intel PT, specifically, as we will see, by using its PT-write packets. And Intel PT is a very low overhead tracing facility, as I will explain in the next slide. And then when the execution is finished, TMon analyzes the trace data to decide whether the trace execution exhibited a data race. And despite TSan, we do not perform any data race detection analysis as runtime. Everything is postponed to post-mortem analysis. And as I mentioned, TMon has no direct impact on application memory usage, and it has a very low runtime overhead. Before getting into more details about TMon, let's have a quick review over Intel processor trace. It is a hardware feature, a dedicated hardware feature that generally logs information about software execution with minimal impact. It provides different tracing facilities. The two used by TSan are one, the PT-write packets, which are user-generated 8-byte payloads. They are generated using the PT-write instruction, which sends the value of its operand to the Intel PT hardware to be encoded as a PT-write packet. The PT-write instruction was previously introduced in Atom processors, but now it is widely available in the Alder Lake family, the 12th gen Intel processors. And executing a PT-write instruction is very fast. On our machine, it takes only 2 CPU cycles to execute a PT-write instruction. And the second information that we use in TMon is metadata related to each PT-write packets, more specifically the thread and processor, the process IDs that are related to each PT-write packet. So back to the architecture of TMon, the first question is what to trace. Since the goal is to provide the same level of analysis as ThreadSanitizer, therefore we should be able to trace the same program events that are tracked by TSan. And for each of those events, we should be able to trace the required runtime information that are captured by TSan's data race detection logic. And how to trace them? The basic idea is to use PT-write instrumentation, where the most significant byte of the payload encodes the event type. And since we have less than 255 events, 1 byte is sufficient. And the remaining 7 bytes are devoted to capture the runtime information related to that program events, the information that is needed to analyze that event regarding data race detection. TMon has 3 main parts. We have a compile time instrumentation infrastructure, which instruments user code. We have a static library, which intercepts a specific library functions, more specifically the ones that either cause a timing constraint within program events or access memory. And we have a post-mortem analyzer, which analyzes the trace data, as I have already mentioned. So I start with the implementation of our compile time instrumentation. We instrument user code at LLVM IR level. We have written a function path to do that, which basically its goal is to identify and instrument different types of memory accesses within user code. And as we will see, sometimes it is also required to instrument function entry and exit points to be able to generate detailed reports in case of having a data race. Our function path has 5 main tasks, which I will go through one by one. It first decides if a function is eligible to be instrumented. And what it basically does is that it checks if each function has one of these 2 attributes, which in such case the function is exempted from any instrumentation. The first function attribute is the naked attributes, which indicates the absence of standard prolog and epilogue sequences, and therefore generally it is not able to instrument function entry and exit points for such functions. And similar to TSan, TMon leaves such functions uninstrumented. And the second attribute is something defined by TMon, disable TMon instrumentation. It is basically designed to provide programmers with the flexibility to selectively leave certain functions of their choice uninstrumented, and it is worth noting that TSan also provides a similar function attribute. So here we were trying to follow the same behavior as TSan. So when a function qualifies for instrumentation, the path basically goes through every instruction in a function, and the instructions that are engaged in accessing memory. The important thing here is that TMon targets the same set of instructions as TSan, which are non-atomic and atomic memory accesses. However, it can be proved that for some non-atomic memory accesses, instrumenting some of them can be redundant regarding data race detection. TSan detects 3 such redundancy cases, which the first one is a read before write happening in the same basic block when there is no calls happening between them. It can be proved that in such cases the read instruction can be safely excluded from instrumentation, and the write instruction is marked as a compound access. The second case is reading an address that points to a constant data, and since it's not possible to write to a constant data, so it cannot form a data race, so it is safe to leave them uninstrumented. And similarly, the third case is accesses to addressable variables that are not captured. And since such variables cannot be referenced from different threads, so they cannot contribute to a data race. And with TMon, we also perform the same 3 redundancy checks. And the important thing to remember here is that as a result, at the end, TMon instruments exactly the same instructions as TSan. So here we get to the actual instrumenting approaches taken by TMon and TSan. First, I will explain how it is performed by TSan, and then I will explain our approach. To instrument non-atomic memory accesses, TSan inserts a call to a specialized runtime library function immediately before the access happens. And that function is basically where the data race detection logic is. For analyzing non-atomic memory accesses, TSan's logic requires to obtain 6 properties pertaining to each access, which is one access type, whether it is a read or a write operation. The access size, TSan supports 5 different sizes, 1, 2, 4, 8, and 16 bytes. Any instance of a memory access other than these sizes are not instrumented by TSan. It checks whether it is an aligned access or not, for if it is a compound access, as explained in a previous slide. If the access is to a volatile memory location, and finally the access address. The first 5 properties contribute to a total of 50 different types of non-atomic memory accesses. TSan supports 50 different types of non-atomic memory accesses. And the approach taken by TSan to encode the first properties is to employ a dedicated instrumentation function for each case. For instance, it uses the library function TSan read1 to instrument non-volatile read operations of size 1 byte. And the last property, which is the access address, is passed to the corresponding instrumentation function as the sole argument. In TMon, we insert a single PT write instruction immediately before the access happens. We support exactly the same 50 different types of non-atomic memory accesses. And for each of those accesses, we trace exactly the same 6 properties for each access, which is achieved by dedicating the most significant bytes of our 8-byte payload to cumulatively encoding the first 5 properties, like by allocating 50 unique values. And you can imagine that as each of those values being exclusively associated with one of the 50 runtime functions used by TSan to instrument non-atomic memory accesses. And then we use the 6 least significant bytes of the payload to store the last property, which was the access address. And since we are instrumenting exactly the same non-atomic memory accesses, and for each access we are capturing the same runtime information captured by TSan, therefore our post-mortem analyzer is able to perform exactly the same data race detection analysis performed by ThreadSanitizer for non-atomic memory accesses. For atomic memory operations, TSan takes a similar approach. It serves a call to a specialized runtime library function, but here the difference is that for each operation it needs to obtain 3 properties. One is operation type. TSan supports 4 atomic operation types: atomic load, store, read, modify, write, and compare and swap. The second property that needs to be captured is the access size, which is the same size as supported for non-atomic memory operations. And the third property that needs to be tracked is the access address. And again, here the first 2 properties contribute to a total of 20 different atomic operations supported by TSan. And similar to non-atomic operations, TSan encodes the first 2 properties by applying a dedicated runtime library function for each case. For instance, the runtime library TSan atomic 8 load is used to instrument atomic load operations of size 8 bits. And again, similar to non-atomic memory accesses, the last property, which is the access address, is passed to the corresponding instrumentation function as the sole argument. In TMon, again, similar to non-atomic memory accesses, we instrument each atomic operation by inserting a single PT write instruction right before the operation happens. We support exactly the same 20 different types of atomic operations. And for each atomic operation, we trace exactly the same 3 properties captured by TSan, where the most significant bytes of the PT write payload that we are using is used to decode the first 2 properties. And again, you can think of them as having 20 unique values, each responding to one of the 20 instrumentation functions used by ThreadSanitizer. And we use the 6 least significant bytes to encode the access address. And again, similar to non-atomic memory operations, since we are instrumenting exactly the same atomic operations is TSan, and for each operation we are recording exactly the same runtime information captured by TSan's data race detection logic. Our post-mortem analyzer will be able to apply the same analysis carried out by TSan. And finally, sometimes it is required to instrument function and entry and exit points, specifically when we have a function which contains instrumented memory accesses. And the reason is that in case we have a data race with that access, we should be able to report the stack trace. So what TSan does is that it inserts a call to TSan function entry with the return address of the current function passed to it, and it just marks the function exit with a dedicated library function, TSan func exit. And in TMon, we follow the same behavior. For inference, we insert a single ptwrite instruction right at the beginning of the function with its most significant bytes of a payload indicating that we are entering a new function, and with the 6 least significant bytes storing the return address of the function as done by ThreadSanitizer. And similarly, for function exit, we instrumented with a single ptwrite instruction whose most significant byte of a payload indicates that, okay, we are exiting the current function. And here's an example of TMon versus TSan instrumentation of the user code. On the right, we have TSan instrumentation calls to function in 3 different read-write runtime library functions, and on the left we have the instrumentation resulted by using TSan at LLVM IR level. And as you can notice, for each TSan instrumentation we have an equivalent ptwrite instrumentation in TMon. The second part is intercepting specific library functions, the ones that either impose a timing constraint or cause a memory access. Most significantly, we need to deal with pthread functions, which are highly integrated with the internal data race detection logic in TSan. And they are either defined as a static or shared library depending on the compiler. And here we can see the general scheme of TSan interceptors. It's inside the interceptor we have a call to the real function, and then the updating of the status of the race detection logic, which happens on the run. TMon employs interceptors as well, but the difference with TSan is that again, we do not have any data race detection at runtime. But our interceptors are just meant to record required runtime information, again using a ptwrite packet. And what needs to be recorded with library functions generally depends on the function being intercepted, but generally it is usually some attribute passed to the function and the return value. And similar to TSan, we use a simple interposition to redirect such function calls to our own implementation, where each interceptor has a weak alias of the same name as the intercepted function. And our interceptors are defined as a static library. And here is the general architecture of our interceptors. We just need to record the required runtime information. Again, no data race detection analysis at runtime. So we usually have, similar to TSan, the call to the real function, and then using a ptwrite instruction to record the required runtime information regarding that function call. Like if we are, let's say, calling pthread join, we indicate that, okay, we have a pthread join call, and this is the thread that we are trying to join here. And our post-mortem analyzer, the final part, as mentioned earlier, its goal is to process the trace data to determine if we had a data race with our execution. So what it basically does is that it uses the information encoded within PT-write packets to reconstruct the sequence of program events. It is built upon the data race detection logic used by ThreadSanitizer. In fact, we use great parts of the TSan RTL, which happens before algorithm, a well-known algorithm in the data race detection logic area, which is basically based on the happens before relation proposed by Lamport for distributed message passing systems. But we also introduce some novel algorithmic contributions to enhance the race detection coverage. Our suggestions are aiming to mitigate data race detection loss in TSan. TSan uses what it calls shadow cells to keep track of memory accesses, where every 8 bytes of application memory are mapped to 4 dedicated shadow cells, with each shadow cell encoding an access to that memory region. And upon detecting a new access, what happens is that it is compared with the ones already encoded with shadow cells to detect if they form a data race. But the problem with shadow cells is that at some points we run out of a free shadow cell, so we have to overwrite one of them, which means losing information about a previous access and the possibility of missing a data race. And TSan just takes a random selection strategy to override a shadow cell. So in TMon, first of all, since it is a post-mortem tool, it is simply possible to allocate more shadow cells. We adapt a post-mortem adaptation of the shadow cell. So by allocating more shadow cells, we can reduce the need to overwrite a shadow cell. And the second improvement is just to take a better overriding policy. Like in TMon, if we need to override a shadow cell, we select the one which is associated with the access that involves at the least number of bytes, because by following such approach, it reduces the risk of overlapping with subsequent accesses and therefore missing a possible data race. And it might be interesting to note that the same approach can be also applied to ThreadSanitizer. And here are our latest results using a Fourier transform benchmark with a different number of threads and different number of input values. We have measured the execution time for each case and also the memory overhead. And as we can see, on average, using ThreadMonitor was about 10 times faster than using ThreadSanitizer regarding execution time. And while TSan imposed on average 5-time memory overhead, we do not have any direct impact on application memory. But of course, since TMon is a post-mortem tool, there will be an overhead for analyzing the trace data, which was completely tolerable at least for this benchmark. And the thing to also should be noticed here is that the overhead reported for TMon, it includes everything, including the overhead of collecting trace data and writing them to disk using Linux perf. So our conclusion in this presentation, we presented TMon, which is a low overhead post-mortem data race detector for C++ programs. The main idea is to use low overhead PT-write instrumentation, whose 8-byte payload encodes the required runtime information to perform a data race detection analysis after the execution is finished. And as I mentioned, TMon has much less runtime and memory overhead compared to TSan. And as a possible future work, we will be investigating the possibility of applying a similar approach to design other post-mortem tools that emulate other verification tools such as ThreadSanitizer. Thank you very much for your attention. Questions or comments?
Questions, anyone? One, two.
Thanks for the talk. It's very interesting. You mentioned that, the way I understand it, you use PT-write essentially as a lower overhead way of writing. But could you do maybe with a bit higher overhead, use a ring buffer, and then that would work also on older processors? So is the only reason you use PT-write only to reduce overhead? Yeah. Or is there another reason that I missed?
The only reason was to have a low overhead for tracing. But if you have like another tracing approach which can collect the same runtime information as what is currently being collected by TMon, you should be able to use our post-mortem analyzer to analyze your traces. So PT-write was just a mean to have low overhead tracing.
Thanks for the talk. Can you go back to slide 27? So you said you enhanced the coverage through introduction of novel algorithm. I know for a fact that TSan does not support thread fans very well. Do you plan to support them in TMon or to improve the TSan algorithm to support thread fans? Because a lot of code can have data arrays. Yeah. Use thread fans, and this type of code doesn't work with TSan very well.
I see. You know, our first goal was to first have everything that is already provided by ThreadSanitizer to be able to emulate the same behavior, but it might be a possible future project to have add-ons to what TSan already has. So we do not support it for now, but it might be something interesting to look into. Yeah.
I have one question as well. You mentioned that you issue the PT writes before the memory operations. Yeah. My concern here with that choice is if you have, let's think about a happen before relationship. So we have a store release and a load acquire that are paired together. If you issue the PT write before the store release and before the load acquire, I expect there might be false positive because the PT write before the load acquire might be issued with a timestamp that happens before the load acquire dependency is actually issued by the system.
2 points here. First, again, we were trying to emulate the same behavior as TSan. TSan instruments memory accesses right before they happen, so we just took the same approach. And that the second point here is that the happens before is a logical timing relation. It's not a physical timing relation. So it probably covers what you just mentioned because we're not working with timestamps. But for different accesses, we check if it can be proven that one access is constrained to happen before another access because of the existence of a synchronization or mutual exclusion. Yeah. So we're not...
Yeah, what I'm unclear about the details is whether TSan issues the atomic operation with some internal locks taken that protects the memory cell. In your case, you don't have that. Where I think TSan might be right in whatever order because of internal locking. So in your case with tracing, it might be important to do things in the right order. So maybe we can take that offline, of course. But yeah, I mean, this is something that kind of bothers me. Maybe in some cases for atomics doing before and after PT writes, and for happen before relationship doing the load acquire instrumentation after might be important.
Okay, yeah, it might be the case. Yeah.
One more question.
It's really a comment on your comment that even if it was using timestamps, because it's only issuing PT writes where it's when the read or write is non-redundant and in the same basic block, even if there happened to be a huge gap, seconds between the PT write and the data operation, there's still a potential data race because that gap is schedule dependent and might or might not happen at any given moment. There might not have been an actual corruption at that instance, but there's a guaranteed race, it seems to me. Because the delay could be arbitrarily short. It might be basically zero, and you don't know what else is happening at the same instant. So I think you'd be safe even if there was I think it would be a correct answer, even if there was it was using actual timestamps rather than happens before. We've run into this in dtrace.
That could be an interesting topic for on conference. Yes. So that's all the time we have for questions. Thank you very much.